Our first speaker is Dr. Alexandra Belayew, and she is going to be giving you FSHD 101.
So I would like to welcome all of you in this strange field of FSHD science. So I have the very delicate task of sort of explaining the basics of FSHD. And so I want first to thank the FSH Society for having invited me here. The scientific meeting that just finished was very exciting, and I hope we can convey part of what has been said among scientists to all of you during this meeting. So let's get started, if I can get this to work. Yes. So we start very simple. Every one of us is like this yellow little man, constituted of a very large number of cells. Now, to the right of this, to the right of this slide. So I'm a bit frustrated because I'm a teacher and I'm used to walk and make large moves in front of my screen, but with two screens, I don't know what I should do. So I will try to tell you, look right, left, up, down in the slide to know what I want to talk about. So the cell, which is drawn to the right, bottom of your slide, has a little gray part in it. This round gray part is named the nucleus. And that's where the chromosomes are located. So you know very well that we have humans, we have 23 chromosome pairs. And why pairs? Because for each chromosome you received a copy from your father and a copy from your mother. You're most familiar with this problem of pairs of chromosomes relating to your sex. So if you have received an X chromosome from your father and an X chromosome from your mother, you're a woman. If you have received the X chromosome from your mother and a Y chromosome from your father, you are a man. So these chromosomes are familiar to you. But probably even more, chromosome number 4, the one where you have the little yellow flash pointing to, this is the chromosome 4 pair. And on one of those two chromosomes is the genetic defect of FSHD. So let's have a closer look at chromosomes. What are they made of? Where their main constituent is DNA. And you all know very well the beautiful double helix structure of DNA that was discovered a long time ago by Watson and Crick, and for which they got the Nobel Prize. Now let's go further closer to this double helix. We realize that each strand of the double helix is a long chain that is made by linking 4 different chemicals that I will name the letters. These chemicals are named A, G, C, T from the chemical name. We will use only the first letter, not bother you with the rest of the word. Now, what is interesting is that just like in the English language, where it's the order of the letters that defines the information in the words that you are spelling, the sentences that you are saying, here also in DNA, it's the order of the letters, these AGCT letters, that defines the information that is on DNA. Now, what is interesting is that we have 2 chains. They are said to be complementary. Why that? Because there's a very simple rule. When you know the order of the letters on one chain, something which is named the sequence of the letters, you automatically know the ones on the other chain. The rule is simple. Each time there's an A on one chain, you have a T on the other one. Each time there's a G on one chain, you have a C on the other one. And with this simple rule, if there was some kind of accident occurring to one of your DNA strands, well, it can be rebuilt by your cell using the information which is on the other strand with this simple rule, A in front of T, G in front of C. So now you know what is a chromosome, you know it's made of DNA, and we have to define what is a gene. Well, a gene is just a DNA segment in which the order of those letters states the recipe to make a protein. All right, but what is a protein? Well, basically our body is made of proteins, many different proteins. And this little lady has pointing to her little text showing the different proteins, the most important proteins, which are found in the different parts of her body. I know for people sitting at the back, it's written too small, you cannot read it. It doesn't matter. I will just point a few of them. The idea here is to show you the variety of proteins that we have in our body. So for instance, hair and nails, we have a major protein which is named alpha-keratin, which is making hair and nails. There's another protein you probably heard of, which is named hemoglobin. It is found in your bloodstream, and this protein goes to your lungs, where it takes oxygen when you are breathing, and hemoglobin carries oxygen everywhere in your body, including in your muscles, including in your brain, and that allows you to listen to my story. Now, you are mostly interested in muscles. So in muscles, you have two proteins which are very important, which are named actin and myosin, and these two proteins can slide on top of each other, and when your muscle is contracting, they slide, and this is providing you with the strength you have when you exercise. So I will stop here with those proteins, or maybe one more, is that you probably got an injection against the flu, so vaccination against flu. So this is supposed to trigger production of another type of proteins, which are named antibodies, and that will block the virus if you ever get in contact with them. So another type of protein. Well, basically, many different proteins. To make things more simple, I decided to compare proteins with cookies. And you know that cookies can come in a large variety of shapes and colors and all that. So these are typical local cookies. And when I gave the same talk in Italy recently, I had different shapes of cookies because the Italian cookies are different from ours. You know that very well. So we can now make things very clear. The gene is the recipe to make a cookie. So where is this recipe? It's located on the chromosomes, because the chromosomes are made of DNA and the gene is a segment of DNA. And the nucleus is like a central library. There you have all the books with all the recipe to make all the proteins in your body. But, like in some libraries where you have a very strict control on book transport, the DNA is not allowed outside of the nucleus. So all the recipe books have to stay in the nucleus. But how can the cell manage to have the cookies made if the recipe stays far away from the kitchen, from the bakery? The idea is that the gene will be copied into a molecule that is named a messenger RNA. And you see it below the nucleus. This messenger RNA has the right to get out of the library. It's like a Xerox copy of your recipe can go out of the library, although the major book cannot go out. The messenger RNA will travel in the cell, go to the bakery, where it will bring the recipe to make the cookie, and the cookie will be made. It's presented here as these little yellow dots. Now, some scientific names. The copy of the gene into a messenger RNA is named transcription, and the use of the recipe on the messenger to bake the cookie, to make the protein, is named translation. Now, let's have a look at a cookie. Very nice cookie. You have a whole collection of cookies. You can have some cookies which are chefs. And these cookies are very important because you have so many different proteins that need to be made in your cells. And these cookies have to be different. These cookie proteins are different if you look at the muscle or if you look at the brain or at your skin. So you need to get things organized. And you have special cookies, special proteins, which are chefs. They organize everything. They decide which cookies have to be baked in the cell at what time. That is, which are the genes that will be copied or not copied, so switched on or switched off. In the bakery, the staff is organized. You have chefs, like chef number 1, can give orders to chef number 2 and 3. Chef number 3 can give orders to chef number 4, and so on. So everything has to be really strictly well organized. Now imagine you have a crazy chef coming into the kitchen. This chef receives orders from nobody and gives orders to chefs that have normally nothing to do in the bakery. Now imagine in your muscles, suddenly there appears a crazy chef that will give orders to muscle genes not to be copied, and will give order to testis genes to be copied. It will obviously create chaos in your muscle. This is exactly what's happening. Oh, there's a pointer, but it's not helping me. I cannot point on the... Okay. Thank you, that's very sweet. I think everybody can follow. Okay, so there we have a crazy chef. And in fact, your crazy chef is named DUX4. And its problem is that it activates testis genes in muscles, which creates chaos. And DUX4 is toxic at all levels in a muscle cell. So every spot where I've put this little, what's the name, like a flashlight, little yellow flash, is showing at which level DUX4 is toxic. It's toxic because it activates genes that do not have to be copied in muscle. It's toxic because it is also altering the way the messenger RNAs are made. It is also toxic because it blocks the quality control system that we have in our cells to make sure the messenger RNAs are of good quality and the proteins which are of poor quality get destroyed. This is also prevented by DUX4, so it's really giving chaos everywhere in the muscle cell. Okay, now we are going to get interested in what are the conditions to develop FSHD. The first condition is a genetic condition, and you basically already know it. We need a DUX4 recipe, so we need a DUX4 gene. And this gene has to have an AND. We will see why. And then it will be able to produce the toxic protein. So let's go back to the set of 23 chromosome pairs. We focus on the end of one chromosome 4, where is the genetic defect for FSHD. What do we find there? So the horizontal line is presenting the DNA of that chromosome close to the end. And some of you can see the numbers, very large number, like in hundreds of millions. These are the number of letters on the chromosome, starting from the other end of the chromosome. We are reaching now this end. And so it's something that is really giant. And on there, the arrows are presenting genes that have been identified in that region. So ANT1, FRG1, TUB4Q, FRG2, these are genes which are found in this region. Now, the genetic defect has to do with what is to the extreme right of the drawing, close to the end of the chromosome, which is named the telomere. You have all those little arrowheads, which are repeated and named D4Z4. So there is a segment of DNA, which is about 3,300 letters long, which is repeated just like a stuttering. Okay? So it's repeated over and over again for a number of times that is different from one person to the other, that is different from one chromosome 4 to the other. And what happens is that the DUX4 gene can be found inside of those repeated elements. So this is something very unusual, to find a gene in repeated elements. All the other genes in this drawing are like nice arrows, single arrows. And that's very special for DUX4. Now, let's zoom on those repeated elements. So the link to FSHD was identified in the 90s, so that's a long time ago. So below my drawings, you will see each time the name of a scientist and the year in which the publication came out, which did those studies. So what was found is that in people with FSHD, there was a decreased copy number of these repeated elements. And then Jane Hewitt, who was working in England, identified within each of those repeated units a recipe that could potentially make a protein. But she did not find a beginning or an end to this recipe. And then people from my group, and in collaboration with Alberto Rosa, who is from Argentina, we identified the beginning of the recipe. So we have a beginning of a gene, and the recipe in each D4Z4 unit, but no end. And finally, the end was identified by a researcher in my group, Eugénie Anceau, who is a very shy person sitting at the very back of the room over there. And Eugénie, can you lift your arm, please? Okay, there she is. So she unexpectedly identified the end of a DUX4 gene, which is shown here in red, which is named poly-A signal. This is something special, a few letters on DNA, that define that the messenger, when it is made by copying the gene, will receive a long N made only of A's. 200 A's have to be bound at the end of the recipe, and this will allow for the messenger to be stable, to have time to travel from the nucleus to the bakery to get the recipe used to make the DUX4 protein. And a large consortium, 6 international laboratories directed by Sylvain van der Marel, who is sitting there on the first row, and you will hear him later, were able to demonstrate that this end of the DUX4 gene was necessary to develop FSHD. So it's a very important issue to have this end. And the persons who have on their chromosome 4 this poly-A signal are said to have the 4qa allele. What does allele mean? Allele means it's one version of chromosome 4. So our chromosomes from one person to the other are slightly different, and so we each have small variations in the chromosomes, and those who have a chromosome 4 with this poly-A signal are said to have the 4qa allele. What does it mean? 4qa allele means that when the DUX4 gene is copied to the messenger RNA has this poly-A tail, it is stable, it can go to the bakery to get the toxic DUX4 protein made. Now, people who have another version of chromosome 4, where this poly-A signal is not present, they are said to have the 4qb allele. And these people will have a messenger RNA for DUX4 that does not have the poly-A tail, that is unstable, that will be destroyed. Look at the red crosses. And so if the messenger is destroyed, the protein cannot be made, and there is no DUX4 protein expression, there is no FSHD. Okay? So this was the genetic condition to develop FSHD. You need a full DUX4 gene with the recipe, with the start, with an end, and this will allow for the toxic protein. But that's not enough. You have, in addition, a requirement for an epigenetic condition. Epigenetic means around genetic. So you're not changing anything in the order of the letters on DNA, but you are changing the way you can access them or not. So the DUX4 gene is said to be has to be in open chromatin to develop the disease. So what does chromatin mean? We look at the chromosomes again, we focus on one chromosome, and look at the right of the picture, you have naked DNA, the Watson-Crick double helix. If you stretch out DNA that is from one chromosome, you will get, of all the chromosomes of one cell, you will get a string that is as high as my self. You have to fit that in a chromosome that is so small, in the nucleus that is so small that you can only see it with a microscope. So DNA has to be compacted like 10,000 times. And in order to compact DNA, it has to associate with proteins which are named histones. And the association of DNA with histones make these nice little beads on a string. The string is DNA, and the beads are the association of histones with DNA. So this string with the beads will wrap up in a helix and finally get into the size required to fit in a chromosome. So the association of DNA with proteins, the structure of beads on a string, can be either open, so this association of protein and DNA is named chromatin. It can be open, active. That means the distance between the beads is large enough, DNA can be accessed by the copy machine that will make the messenger RNA to bring the recipe to build the protein. But it can also be compact inactive. Look here, the beads are close to each other. There is no access to the recipe. The DNA cannot be read, cannot be copied. And how do you change this? There is a small chemical named a methyl group that will go onto the C letter. Look at the C letter. I've put a little round dot, red dot on top of it. And you see on the drawing at the bottom of inactive chromatin, all those little red dots indicate that the DNA is methylated on its C. And when you have that, you have compact chromatin. Now, epigenetics means this is something that is dynamic. You can go from open or closed chromatin by activity of various enzymes. So these are other proteins in our cells that can open up opaque chromatin. And among those enzymes, two are very important for FSHD. One is named SMCHD1, and the other one, DNMT3B. So these proteins will compact chromatin. And normally the DUX4 gene is hidden. Methylated DNA, compact inactive chromatin, no RNA, no DUX4 protein is made, no FSHD. And the SMUSH1 protein is bound to it, and it blocks everything. This was studied mostly by Sylvain van der Marel and Stephen Tapscott. Now, in FSHD, the DUX4 gene is not hidden anymore. DNA has a low methylation, chromatin is open, the DUX4 protein is made. There is hardly any SMUSH1 protein around. Okay? So, conditions for FSHD development, the genetic condition, you need the full gene with the end. Epigenetic condition, you need DNA hypomethylation, that is very few methylation on the DNA, which causes open chromatin, and DUX4 gene can be copied, can be transcribed. In FSHD1, how do you get this open chromatin? By reducing copy number of D4Z4 by a mechanism that is still not clear. In FSHD2, by mutation in those two enzymes, either one or the other, SMUSH1, which is on chromosome 18, and DNMT3B, whose gene is on chromosome 20. Okay? So that's the story. And basically, DUX4 is a crazy chef and a muscle killer. And the idea is to get rid of it. And there are many ways of going after this problem. And scientists at this meeting have shown different strategies. Some will try to work on the gene, some will try to work on the RNA, some will try to work on the protein to prevent production of DUX4 protein or to prevent it from exerting its toxicity. And so it's not clear which of those strategies will work. Maybe several will work, maybe you will have to use several drugs simultaneously, but the target now is well known, it's DUX4. So at the end of this talk, you should know what are chromosomes. They're made of DNA. Genes are segments of DNA. Alleles are two different versions of one chromosome or a gene. You know that the genes are copied as messenger RNA that carry the recipe to make the protein. Among those proteins, you have the crazy DUX4 chef. You know to develop FSHD, there is a genetic condition. You need to have the DUX4 gene, which is located in the last unit, so it can have an end. And you know the epigenetic condition is that you have to have DNA hypomethylation, so not many methyl group on DNA, and open chromatin to allow for expression of the DUX4 crazy chef. So thank you for your attention.